In the grand four-decade chess match of the Cold War, the United States Navy held one advantage to be absolute. It was a strategic, asymmetrical, and seemingly permanent dominance. This advantage was not in numbers nor in speed. It was in silence. The deep ocean is a battlefield of acoustics. Victory belongs to the one who can hear without being heard. And the United States, with its vast undersea sensor networks and its generations of quiet submarines, was the undisputed master of this invisible domain. But in the 1980s, in the twilight of the Reagan era, that supremacy did not just erode, it was precipitously challenged. America's assumed dominance suddenly looked vulnerable. This shock, born of betrayal and illicit technology, triggered a strategic panic in the Pentagon. It forced the Navy to initiate an urgent, near-blank-check push to build a new apex hunter-killer, a submarine so advanced it would be a moonshot in undersea engineering. This was the Seawolf-class SSN-21. It was designed to be the perfect weapon. But the Seawolf became what history would call a perfect failure. It was an engineering masterpiece made politically indefensible, a multi-billion-dollar solution for a war that vanished with the fall of the Soviet Union. The program was slashed, canceled, and relegated to a historical footnote. Or so it seemed. A $3 billion a copy, perfect failure. But that is not the end of the story. It is the beginning. This is the story of how that perfect failure was secretly salvaged, how its final canceled hull was clandestinely re-engineered into the most advanced spy submarine in history, and how that secret, one-off prototype created a hidden continuity, a technological bridge to the 21st century. This is the story of how a secret weapon, conceived in the Cold War, was hidden in plain sight for decades, its design philosophy only to be mass-produced and built into the fleet today as the unspoken foundation of modern American undersea warfare. To understand the Seawolf, one must first comprehend the panic that birthed it. The strategic calculus of the Cold War at sea rested on a single fundamental American advantage: acoustics. U.S. submarines were quieter than their Soviet counterparts, and U.S. sonar systems were more sensitive. This acoustic supremacy allowed the U.S. Navy to dominate the undersea domain. In the 1980s, this advantage was dangerously narrowed, creating a strategic shock that would directly lead to the urgent near-blank check push for the Seawolf-class. In the early 1980s, the Soviet Union executed one of the most devastating technological acquisitions of the Cold War. It was not achieved through traditional cloak-and-dagger espionage, but through illicit corporate sales. A conspiracy was uncovered involving Toshiba Machine of Japan and Kongsberg Våpenfabrik of Norway. These companies sold sophisticated 9-axis computer-controlled propeller milling machines and advanced numerical control devices directly to the Soviet naval shipyard. This was a flagrant violation of the COCOM agreement, the Coordinating Committee for Multilateral Export Controls, which was the West's primary tool for forbidding the transfer of critical military-use technology to the communist bloc. The scheme was masked by falsified export permits, with the companies claiming the equipment was for non-military purposes. But the true destination was a Soviet naval shipyard. The impact was a strategic shockwave. It was catastrophic to U.S. intelligence. This equipment gave Soviet shipyards the one precise capability they had always lacked: the ability to machine submarine propellers with complex, highly skewed geometries. The art of making a propeller quiet is in its shape. The Soviets, using their older, less precise machinery, produced propellers that were, by comparison, noisy and inefficient. The new Toshiba mills allowed them to create blades that were exponentially quieter. This technology struck at the very heart of the U.S. Navy's entire anti-submarine warfare, or ASW, doctrine. That doctrine was predicated on identifying and tracking the unique, noisy acoustic signatures of Soviet propellers. The U.S. Navy had spent decades building a global sound library of every Soviet submarine class. Now, that entire library was being rendered obsolete. The political fallout was immense. In Washington, congressmen, in a fit of public rage, smashed Toshiba products with sledgehammers on the steps of the Capitol. In Japan, the prime minister was forced to condemn the corporation. Toshiba machine has betrayed Japan. But the true damage was strategic. The scandal demonstrated that the COCOM blockade was broken by the profit motives of allied corporations. This failure meant the U.S. could no longer rely on restricting Soviet technology. It would have to create a new generation of weapons so advanced it could outpace any illicit gains. This realization provided the political and strategic desperation necessary to greenlight a program with an extraordinary funding mandate, the Seawolf. The Akula-class submarine, Project 971 Soviet, was the direct and terrifying result of this illicit technology. For decades, Soviet submarines had been engineered for different priorities, but this performance was historically crippled by one glaring flaw: unsuboptimal acoustics. The Akula generation upended this calculus. Using the new Toshiba mills for superior propellers, as well as incorporating advanced active noise cancellation and extensive interior sound dampening measures, the Soviet Union went from a crippling acoustics disadvantage to being able to trade stealth performance blows with the competing U.S. Los Angeles class. This quantum leap occurred within the span of a single submarine generation. The shock to the U.S. naval establishment was profound. The Navy's entire sense of self, its core identity as the silent service, was shattered. For years, the horrifying reality was hidden behind classified briefings. But in 1995, the truth became public when the Chief of Naval Operations, Admiral J.M. Borda, was forced to reveal the improved Akula was in fact quieter than the latest U.S. improved Los Angeles-class submarines. This admission was staggering. The United States had lost what had long been touted as the primary and most important U.S. advantage. The Akula was not merely a quiet hunter. Its ability to carry up to 12 Granat land attack cruise missiles made it a strategic first strike threat that could approach U.S. shores undetected. This comprehensive quieting rendered the U.S. Navy's entire passive sonar doctrine deeply vulnerable. Imagine you were the captain of a U.S. Los Angeles-class submarine in 1988. In a duel between your submarine and an Akula, you are just as loud or perhaps louder than the hunted. This created a hunter becomes the hunted scenario. For you to find that silent Akula, you would have to use your active sonar, an act of tactical suicide. It is the equivalent of lighting a flare in a dark forest. The U.S. Navy was for the first time doctrinally blind. It desperately needed a new submarine that was not just quiet, but orders of magnitude quieter. This tactical crisis was dwarfed by the strategic one. The U.S. and NATO's primary defense was the Sound Surveillance System, or SOSUS, a tripwire, a vast top-secret network of fixed hydrophones concentrated in the GIUK Gap, the only gateway for the Soviet Northern Fleet to break out into the open Atlantic. SOSUS worked perfectly against those older generations, but SOSUS was a fixed passive system. The giant leap forward in acoustic performance from the Akula and the new Delta IV ballistic missile submarines
rendered this critical multi-billion-dollar strategic asset potentially obsolete. The acoustic parity achieved by the Soviets meant their new quiet submarines could now slip through the GI-UK gap completely undetected. The tripwire was broken. This failure meant the U.S. could no longer wait. The U.S. Navy now had to adopt a far more aggressive forward strategy. The existing Los Angeles-class was too loud to survive in the Soviet backyard. Therefore, the Seawolf SSN-21 was conceived as a mobile, offensive replacement for a failed, static, defensive network. It was not just an attack sub. It was designed to be the new GI-UK gap, capable of going on the offensive deep inside enemy territory. This existential crisis is what justified the extraordinary funding and extreme urgency behind the SSN-21 program.
In response to the acoustic crisis, the U.S. Navy initiated the Seawolf-class program. This was not an upgrade. It was a moonshot. It was designed with a cost-is-no-object mandate for a single purpose: to restore American acoustic supremacy. Its design incorporated three revolutionary technological leaps. To execute the new forward strategy, the Seawolf needed to go deeper than any previous U.S. attack submarine. Its hull was constructed entirely of HY-100 steel, significantly stronger than the HY-80 steel used since the 1960s. The 100 in HY-100 refers to its yield strength, 100,000 pounds per square inch. This 25% increase in material strength, combined with new, incredibly difficult welding techniques, gave the Seawolf-class a classified test depth far exceeding the 1,000-foot class operational limits of its predecessors. Its true crush depth remains one of the Navy's most guarded secrets. This HY-100 hull was not just a defensive measure, it was an offensive tool. Deeper diving capability is a form of acoustic stealth. The ocean is stratified, creating shadow zones. A submarine that can operate in these extreme depths has far more operational battle space to maneuver in. It can place itself below these acoustic layers, effectively becoming invisible. The HY-100 hull was the Seawolf's first new weapon system. It weaponized the water column itself. The Seawolf's acoustic trump card was its propulsion system. Powered by a massive new S6W nuclear reactor, delivering approximately 45,000 shaft horsepower, the Seawolf did not use a conventional propeller. It used a pump jet propulsor. To understand why the pump jet is revolutionary, one must first understand cavitation, a stream of tiny hissing bubbles. This noise, cavitation, is a submarine's acoustic death rattle. This means a traditional submarine must choose between speed and stealth. It can be fast or it can be quiet, but it cannot be both. A pump jet works differently. It draws water into a shroud and ejects it at high speed. This physically prevents the formation of cavitation bubbles even at high speeds. The result was a submarine capable of silent sprint. The Seawolf was orders of magnitude quieter than the Los Angeles-class, but its true advantage was tactical. It was capable of silent sprint. It could move at unheard-of stealth speeds while remaining acoustically undetectable. The pump jet's true innovation was breaking the link between speed and noise. Pre-Seawolf combat was a game of creep, where both Los Angeles and Akula subs had to move at 5 to 7 knots to remain quiet. The Seawolf, with its pump jet, could sprint at high tactical speeds while remaining a ghost in the water. This meant a Seawolf could control any engagement, all without ever revealing its position. It was the silent hunter that could move at several times the tactical speed of its predecessors. The brain of the Seawolf was the ANBSY-2 combat system. Its purpose was sensor fusion. to automatically process data from the Seawolf's superior sensor suite, a new larger spherical sonar array, a hull-mounted wide-aperture flank array, and new, more sensitive towed arrays. The BSY-2 was designed to detect, classify, track, and launch weapons at hundreds of targets simultaneously. It was, however, a programmatic disaster. The U.S. General Accounting Office, or GAO, flagged the BSY-2 program as high risk. The BSY-2 program is characterized by immature technology, a high degree of concurrency, and incomplete network security. The ambition of creating a fully integrated automated digital combat system using 1980s computing architecture was a massive overreach. Its costs spiraled into the hundreds of millions. This troubled development is critical. It demonstrates that the apex engineering of the Seawolf and the perfect failure of its cancellation were not sequential events. They were happening at the same time. The Seawolf was already a program collapsing under its own immense technological weight even before its strategic justification vanished. And yet, the submarine that emerged was, on paper, an undisputed masterpiece. When compared directly to the Los Angeles-class, its superiority was absolute. It was faster, a classified maximum speed well in excess of 30 knots, compared to the Los Angeles-class's own top speed of over 30 knots, but the Seawolf could achieve its high speeds far more quietly. It was deeper diving. Its HY-100 hull gave it an operational depth that dwarfed the HY-80 hull, opening up new untapped layers of the ocean for tactical advantage. And it was more heavily armed. It featured 8 660mm torpedo tubes and a massive magazine for 50 weapons. This was double the 4 tubes and around 26 weapon load of the Los Angeles-class. It was, as the head of Navy nuclear propulsion declared after its sea trials, the perfect weapon. The Seawolf was the perfect weapon for a war that would never be fought. Just as this apex hunter was being readied, the world changed, transforming the submarine from a strategic necessity into a politically indefensible liability. The Seawolf was designed with a single clear purpose: to hunt and kill the best submarines of the Soviet Union. The timeline of its demise is a case of historic, brutal irony. In 1983, design work on the Seawolf begins. In October 1989, construction starts on the lead ship. In 1990, as costs begin to spiral, Vice Admiral D.L. Cooper sends a desperate letter defending the absolute need for the SSN-21. The Soviet submarine threat is not decreasing. If anything, it is becoming more and more difficult to counter. In December 1991, the Soviet Union officially collapses. The Seawolf's primary enemy vanishes. In July 1997, Seawolf is commissioned. It is an apex predator with nothing to hunt. The Soviet collapse was the final fatal blow to a program that was already in serious trouble. The popular narrative is that the end of the Cold War killed the Seawolf. The data shows it was more of a comorbidity. By 1990, before the collapse, the program was already suffering from a high degree of concurrent development and lead ship construction, meaning the Navy was building the sub while still designing it. Vice Admiral Cooper's 1990 letter was a desperate defense of a program already under fire from Congress for its spiraling costs. The 1991 Soviet collapse simply removed the last shred of justification for these costs. With no Soviet threat, Congress looked at the Seawolf's price tag and panicked. The cost was staggering: $3 billion per boat. The third boat, Jimmy Carter, would be even more at $3.5 billion. This made the Seawolf the most expensive SSN submarine ever built. For perspective, the workhorse Los Angeles-class cost approximately $1.6 billion in 2020 dollars. The intended successor,
The Virginia-class was specifically designed to be a cheaper alternative. The program was caught in a programmatic death spiral. The original plan called for 29 submarines. When this number was reduced, the massive fixed R&D costs had to be amortized over fewer and fewer hulls. This sharp reduction drove the unit cost to astronomical levels. The final blow came in January 1992. As part of President George H.W. Bush's peace dividend defense cuts, Defense Secretary Dick Cheney ordered the Seawolf program canceled entirely. The Navy, the shipbuilder General Dynamics Electric Boat, and their allies in Congress fought back. They managed to secure funding for the first two boats, SSN-21 Seawolf and SSN-22 Connecticut. The real political battle was for the third and final hull, SSN-23. Ultimately, the 29-boat fleet was officially dead. The Navy was left with just two perfect hunter-killers and no clear mission for them. The Seawolf was overdesigned, overpriced, and completely irrelevant. It was now the most advanced, most powerful, and most strategically useless submarine in the world.
The Seawolf program was a public failure, but in a brilliant and clandestine move, the Navy saved the program's technology by adopting the third, final hull for a new, top-secret purpose. This decision would create the technological bridge that would secretly justify the entire program, and it would all happen in secret. While the Seawolf program was collapsing, the Navy had a secret, looming crisis. Its premier Cold War spy submarine, the heavily modified Sturgeon-class USS Parche, SSN-683, was aging. Parche was a legend, modified for underwater engineering. This was a polite euphemism for espionage missions, including Operation Ivy Bells, the tapping of Soviet undersea communications cables. Parche had been modified with a 100-foot hull extension that contained a bat cave. With Parche's 2004 retirement on the horizon, the Navy would lose this critical capability. The Navy quietly convinced Congress that it needed a replacement. The mission requires a submarine to be exceptionally quiet and stable. A standard Los Angeles class was far too noisy. The new low-cost Virginia class was still just a concept. The perfectly useless Seawolf was in fact the only platform that could do the job. The Seawolf's useless Cold War features were suddenly essential. Its revolutionary pump-jet propulsor offered extreme quiet at low speeds. Its massive S6W reactor provided enormous electrical power for the new mission, including precision thrusters that would allow it to hold its position. The Navy successfully saved the third Seawolf hull, SSN-23, by arguing that its blue water hunter-killer features made it the only submarine capable of taking over the Parche's top-secret underwater engineering mission. The Navy didn't just build SSN-23, they fundamentally re-engineered it. In 1996, General Dynamics Electric Boat was awarded an $887 million contract extension to modify the third hull, which would be named USS Jimmy Carter. This modification was the first plug in modern U.S. submarine history. Engineers cut the submarine in half and welded in a 100-foot-long hull extension. This massive insertion, called the Multi-Mission Platform, or MMP, extended the submarine's total length to a colossal 453 feet and 12,139 tons. This was a profound engineering leap. Parche had been a one-off bespoke modification. The Carter's MMP, by contrast, was a modular insertion. This was an engineering process that General Dynamics Electric Boat, or GDEB, perfected. This plug concept created a reconfigurable space. The Navy wasn't just building one new spy sub, it was prototyping a method for creating any special mission submarine. This was the conceptual leap that would define the future. The MMP is the direct successor to the Parche's Batcave. It is described as having an hourglass or wasp waist configuration. Surrounding this small tunnel is a large, floodable, unpressurized hangar space, a moon pool, variously called the aquarium or ocean interface. This aquarium functions as a hangar and contains the Carter's spy toolkit. ROV hangars, it provides a vast space for remotely operated vehicles and unmanned undersea vehicles, or UUVs. Lockout chambers, it contains facilities for deploying Navy SEALs and can accommodate a dry deck shelter. It also has berthing for up to 50 Special Operations Forces personnel. The seabed interface, the ocean interface, allows the ROVs to retrieve and deploy sensors. This is the unclassified description for the equipment needed to manipulate objects on the seabed, namely, to plant or retrieve wiretaps on undersea fiber optic communications cables. The USS Jimmy Carter is the most advanced, most expensive, and most capable special mission and spy submarine ever built. It saved the Seawolf program by giving its technology a vital clandestine mission. And in doing so, it field-tested the blueprint for the next 50 years.
The Seawolf was the past. The Jimmy Carter was the secret present. The Virginia-class is the future. This is where the 40-year hidden continuity is completed. What the Navy doesn't advertise, but the engineering and strategic evidence makes undeniable, is the direct design lineage from the Carter's plug to the Virginia-class Block 5. As the USS Jimmy Carter was proving the plug concept in secret, the U.S. Navy began facing a new and very public capability gap. The four mighty Ohio-class converted into guided missile submarines, or SSGNs, are nearing the end of their 42-year service lives. This looming retirement represents a massive loss of conventional firepower, each carrying a staggering 154 Tomahawk land attack missiles. All four are scheduled to retire by 2028. Their removal will create what analysts have termed a 60% drop in the Navy's undersea strike capacity. That is a 616 missile gap. The Navy was faced with the same platform versus payload problem. In the 1990s, the Navy was losing a platform, Parche, for a specialized payload, spying gear. The solution was the Carter. In the 2020s, the Navy is losing a platform, the Ohio SSGNs, for a massive payload, 154 Tomahawks each. The Carter's 100-foot MMP plug provided the elegant solution. Do not build a new hyper-expensive specialized class of SSGNs. Instead, modify the existing Virginia-class with a modular plug. The solution is the Virginia-class Block 5. Starting in 2019, the Navy began building Virginia-class submarines using the exact same engineering concept pioneered by the USS Jimmy Carter. The new Block 5 boats are cut in half amidships to add an 84-foot-long plug called the Virginia Payload Module, or VPM. This new hull section adds 4 large-diameter vertical launch tubes for a total of 28 additional Tomahawks. This brings the Block 5's total Tomahawk capacity to 40, helping to plug the 616 missile gap. The engineering lineage is clear. The manufacturing process and the prime contractor, General Dynamic Electric Boat are the same. The 100-foot MMP inserted into the Seawolf hull was the engineering prototype for the 84-foot VPM now being inserted into the Virginia hull. The Seawolf program through the Carter taught GDEB how to build a modular, plug-based submarine. But the VPM is not just a missile module. This is the critical final connection. The VPM is a secret weapon hiding in plain sight, and the proof comes from the U.S. Navy's own fact files. According to the Navy's official description, the VPM is a new hull section that, in addition to adding 28 missiles, also reconstitutes the ability to host dry deck shelters, further enhancing SOF capability, and allows the Navy to host additional advanced payloads via multiple ocean interfaces. Those are almost verbatim the exact special mission capabilities of the USS Jimmy Carter's 100-foot multi-mission platform. The evidence strongly suggests a hidden continuity. The Seawolf SSN-21 served as the technological base for the Carter SSN-23 to create a one-of-a-kind secret weapon. The Navy then used the public budgetary justification of the SSGN retirement to mass-produce the Carter's secret multi-mission plug concept, the VPM, and install it on every new attack submarine. The VPM looks like a missile module, but it is built with the full multi-mission DNA of the Carter's MMP. This means the secret Cold War weapon, the Seawolf MMP concept, is now entering mass production as the VPM. Every new Block 5 submarine now under construction is a potential Jimmy Carter, capable of seabed warfare, deploying UUVs, and supporting massive SOF teams. The VPM is the MMP, standardized and mass-produced. The Seawolf SSN-21 program was born from a moment of pure strategic panic and died a public death from the sudden onset of peace. It was an engineering marvel that became a programmatic pariah, a $3 billion a copy, perfect failure. But this analysis shows the Seawolf program was, in fact, one of the most important and successful submarine R&D programs in modern naval history. It was a masterpiece built for a war that vanished, and yet it became the most valuable R&D platform of its era. In a brilliant move of adaptation, the Navy saved the program's final hull, SSN-23, and transformed it into the USS Jimmy Carter. In doing so, they didn't just create a replacement for the Parche. They field-tested a revolutionary design philosophy, the modular plug. The Virginia Payload Module, or VPM, now being built into every new attack submarine, is the direct engineering descendant of that secret 100-foot plug. The perfect failure of the 1980s provided the secret prototype that is now the defining and most flexible weapons system of the U.S. Navy's undersea fleet today.